Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to continue our struggle in defining line key points, and the description of those line key points were explained in the previous video. Check out those if you have missed it. And of course I want to mention that this is part of two video series linked on the top right, one of them about the theory and the other one about programming. Also, my dear channel members would have access to the entire source code. However, if you are not a channel member, then don't worry, because you could write along and you'll have the exact same code as mine. So with that being said, let's dive into the line key points part 2. So sit back, relax, and enjoy the show. Okay, we are now here in defining the line key points for loads, meaning that I need to cycle through the load cases and cycle through all the loads and do a bunch of shenanigans. So here I would have a for loop for load case index equals 1 to the length. Oh wait, I think I called it load case count. Did I call it load case count? Yeah, load case count, it's there already. So all the way to the load case count, and here we're gonna basically fish out our load case. So here load case equals object, which is the controller, dot stir load cases of load case index. Now we have the load case, which is fine, I guess. Now we need to cycle through all the loads, believe it or not. So for load index from 1 all the way to length of object.str loads. And now we need to fish out the load. So here load equals object.str loads of load index. So now we have the load and we wait, why is there an error here? It's called nodal loads and oh yeah, fine, okay. Which means it's gonna be pretty hard. It's not just loads, it's everything. Okay. Once again, I should have used polymorphism. I don't have it. So now this is called str. Now nodal loads would not create line key points, because nodal loads by definition are applied on nodes. What will create line key points are distributed loads and concentrated loads on the bar. So it's str. I will ignore nodal load. I will go for line load concentrated, and I will do it again. I need to copy paste this entire thing again for distributed. So now let's do it here. We have the load case, but we're not out of the woods because I must filter the loads. Meaning I must check if the load is indeed in that load case or not. So here I'm gonna go for the load. I forgot how I do this. Let me just check very quickly what I defined inside the load. So let me see. Did I define the ID? Yeah, load case ID. Okay, so what we're gonna do is we're gonna ask the question: if the load case ID equals load case.id, then we can proceed. Let's do the opposite. Let's say the load has a load case ID that doesn't correspond to the current load case, then we shouldn't even consider it and we can just continue. Yeah, that makes more sense. I need to push it down here and enter or end. Yeah, my C# is now coming back to bite me. Check if the load is indeed on or defined on that load case. This is one check. Now here another check is check if the load is applied on the stir line, basically, or str line. So how do I do that? Not really hard. I basically define me is applied on line. I'll give it a false here. Now of course here some shenanigans will happen, but in the end, if it is not applied on line, then just continue. We can ignore it. So here, if it's not of the load case, we can continue. If it's not applied on our line, we can continue. But now we need to check if it's indeed applied on the line or not. So here, I will go for another for loop, and I will say here, applied on index from 1 to of all, cycling through all the applied indices of the load. So here, load dot, I think it's called applied on IDs. I need to check if that's the case or not, because this is something that I have defined in ages. Let me check very quickly. Applied to. Let's go applied to. Fine. Now we're cycling through that. I need to check if this line has an ID that is on here. So now you could do it differently in MATLAB. I'm doing something that is also compatible if you want to translate this into C++, for example. So here I will basically fish out the applied on ID by going to the load.applied_to at the applied on index. So we have this now, and now I ask the question, if applied on ID is the line.id. Is it the line? Do I have a line here? Yeah, the line. If the applied on ID is indeed the line, then we found it, and we can basically say is applied on ID. That's true now, and we can break out of the loop because mission accomplished. Otherwise, online, yes. Otherwise, we will stay in the loop and it will always be false. And here we're gonna just break out and continue. Fantastic. Now here we checked, so now we can say it is on the line and it is part of the load case. So now we can start here. Now this is a concentrated load, right? Yeah. Let me write here concentrated load equals load, just for shenanigans, just for fun. Now the concentrated load in the star line is defined in the global sense because the controller and we have only programmed the ability to define loads in the global axis sense, not in the local axis sense. So this is in the global axis sense. However, since we are dealing with internal forces and bending moment diagrams and shear force diagrams, those are calculated in the local axis sense. So I need to take the load and somehow convert it into local. So what I'll be doing is I will go for global loads and basically declare me a vector here. I will put in the concentrated load.fx all underneath each other. It's a column vector here. Concentrated, I think I can just put 3 dots here and make it even more ergonomic. Concentrated load.fy. Those are those. Now I have the global loads. I can use a transformation matrix to calculate the locals. I should declare it here somewhere. So I have the line, right? Now the line itself doesn't hold a transformation matrix. It doesn't have it because it's not a finite element method object. I can declare a transformation matrix and go to the line, go to its fem bars, the first one, and then fish out the transformation matrix. Now you would wonder, why did you choose fem bar 1? Why not fem bar 3 or fem bar 5? It doesn't matter because all fem bars are in the direction of the line because we are not having arcs here. We're just having linear elements, which means that the transformation matrix of the first one is going to be the transformation of everyone. So that's why I have the transformation matrix here, and I can use it now. I can use it on the global loads to find the local loads. I can go here and say local loads equals wait, I forgot. I think I should multiply the transformation matrix without a transpose, right? Let me figure it out. Yes, that's true. So here, because I only have 6 elements, I need to take half the transformation matrix. So transformation matrix of 1 to 6 and 1 to 6, half of it, multiplied by the global loads. So this should give me the local loads. Yeah, so far so good. Now I have the local loads. It's time to define the line key points. There are 2 options for the line key point definition here. Now I could just go in and say LKP equals and define a line key point, but there is a problem. The line key point might have been defined before. And if it was defined, I must modify and add to it. If it was not defined, then I do not need to add to it. The definition of line key points could happen if by chance, by absolute shenanigan chance, the force was applied on the same point where the line key point is. Like the axial load or the point load was applied at the same location where the line key point or the fem bar ended, for example. This is very rare, but possible, so we need to take this into account. Meaning, I would ask here, LKP for now equals nothing, and I will ask here LKP was defined. I will declare it to be false, and now I must search. So to search, I will go for a for loop here, I will call LKP index equals 1 to the length of line.line key points. Because if you remember, every line key point we defined, we pushed inside the line key points. So now I need to check if those line key points hold what I need or not. So let's take a look. Here, how do I do that? Well, it depends on the location, right? Line or LKP location. Now the line key point location depends on the position of the load. So here I will go for concentrated load dot relative location, and I will multiply this by the line dot length. This is the position where the line key point is going to be, because we are going to create it at the position of the concentrated load, which has a relative location, and we have the line length multiplication, we get the line key point. And now I must compare this with every single absolute location here. Let's not fish it out for once. You can say here line dot line key points of LKP index dot wait, what's it called? It's called absolute location. Okay, fine. So dot absolute location double equals LKP location, then it was defined. Now that's not how we do things, because we cannot do equality because of something called numerical accuracy. Let me just put the end here for the if. I cannot simply say equals, but what I can do is I can ask if the difference between those two dudes is very small. And by very small, I mean it's less than the epsilon that I have defined. I don't know, epsilon might trigger all kinds of problems. Let's make it something more than epsilon. 20 multiplied by epsilon. So multiplied by object.epsilon. Because we are not in a case of finite element or stir accuracy, we're just in regular accuracy, so I think this is okay. So if they are at the same location, I will basically flag a flag, and I will say LKP was defined is true, okay? And the LKP I have outside here, this is the line dot line key points at the LKP index. So I found it. I should break out. I don't know, it doesn't matter, but I think I should break out here. Now we finished the check, and here the question becomes if LKP was defined. Now a smarter way of doing things is just to check if LKP is object. But I have two things, so why not? So if LKP was defined, then we're not going to define the LKP, but we are going to add to it. Now this is a concentrated load. It's a concentrated load on the bar. So if the LKP was defined, I will have to basically go and say LKP.fx concentrated at the load case index, because we are cycling through every load case index, if you remember, which is this dude, this outer cycle. Now this is going to equal the old LKP index, the old LKP fx concentrated of load case index plus the local loads at 1, because we have just created the local loads, right? We have it. Okay, there is an error. Why? How you don't see this? Local load. I think I should put an S here. Yeah, now it sees it. Fantastic. So we have it here. Now we need to copy it 6 times because you have 6 things. So, okay, fine. Let's just paste, 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 paste. Now this is the case if it was defined. However, what happens if it was not defined? If it was not defined, then I have to do the same shenanigans of here where I define line key points. So with some differences. So let's do it now. As a matter of fact, I will just make this smaller because I kind of lose track. So here we need to define our new line key point. I will call here LKP equals line key point of, and I think we have LKP distance or something. Let me see, LKP location, LKP location. And for load case count, I have load case count. Do I have load case count? Did I define it in this function? I think I did. Yeah, I defined it. Perfect. Okay. So we defined our line key point. Now LKP.isFE, that's a false, and I don't need to set the flag. I will keep it. I will not set the flag here because there is a chance that it is an FE point too, because maybe it was default. Oh, there is no chance. It's false by default anyway. So here I will start doing my shenanigans, and yeah, I just copy this, right? Right. I just have to copy this entire thing and paste it here to put the stuff. And now I have a line key point. Do I put the line key point, right? I cannot simply say line dot line key points equals line dot line key points and LKP. I cannot do that because I don't know where the line key point is. I want to place it in the correct position. I want to insert it. So where do I insert it? So let's make a loop. For LKP index from 1 all the way to the length of the line key points end. And now we need to check for the absolute location, right? So I'm going to go here and say if line key points of LKP index is more than my current line key point. So LKP dot absolute location. If it's more, then I must insert here and break here. So how do I insert this? This is what I found on the internet. This is disgusting. That's something I thought about already, but I don't like it. Okay, fine. Let's just use it. Okay, so line key points, fine, we win. So from here to here is from here to here and here to here. This index is called LKP index. Okay, and this is called LKP index, and the value is the LKP. Okay, I don't know if it will work or not. Let's put commas here to kind of look more ergonomic and more natural, to look more readable. And yeah, okay, fine. I guess it needs to be debugged. I don't trust this line of code, but well, it does the job, I guess. So okay, now with this we have finished the definition of LKPs for concentrated loads. So for this thing, now we need to define LKP for distributed loads. You know what? Let's do it in this video. You could pause now, go drink a cup of coffee. I'm going to continue. I will copy this load. So for this load, I will copy it. Let me copy it from here to here. Okay, and now enter. And now paste. Okay, so I have, let's Control A, Control I to indent it correctly. Okay, now this is for dealing with stir line concentrated. Now we want to deal with stir line distributed. Okay, so now things change. This becomes stir line distributed, right? Did we call it that way? We didn't call it that way? Really? Line load distributed, maybe? Yeah, that's the one. Okay, fantastic. So now this becomes, I think I should copy and paste the same thing, by the way. So we check again. It is applied. Oh, wait. I messed up. I totally messed up. I don't want to touch this. Let me paste this here and paste this here. And paste this here. Yeah, that's untouchable. We have finished this. Let's not destroy what we have done. But now we're dealing with the distributed. So this is load distributed. What we're doing is we're fishing out the load. We're checking if it's the same load case. If not, continue. We're checking if it's applied. If it's not, continue. And now here, this is distributed load. So let's call it for now linear load. And okay. So now I want the global loads, but wait. This linear load doesn't have fx and fy because it's a trapezoidal load. It has fx1 or fx start. I forgot if it's fx1 or fx start. Okay, it's called fx start and end. So what I will be doing is I'll put dot here, enter, copy this entire thing. Wait, what? Yeah, I forgot to paste here. Copy this entire thing and paste it here and change things. I don't need those 3 dots now. So here, I would say start, and I will copy the start word here and paste it everywhere. Then I will write end here. And that's that. So now we have our global loads. We go to the transformation matrix, this time the full transformation matrix, because it's a 12er, which means we get the local loads. And now, that's dangerous now. We need 2 line key points. It's dangerous now. I need to focus. We need 2 line key points because the load has a start and an end. So I must call here LKP start. Okay. Now LKP start was defined, that's no. And LKP start location is going to equal the distributed load or linear load, relative location start. And now we're cycling through everything and we're checking the start is the same. Let's say LKP start was defined. I don't think I need to push this back because we're not dealing with concentrateds here. So let's not push it back for now because we're dealing with distributed loads. I don't think I need to give this back. So LKP start was defined is true now. And now we ask the question, was or LKP start was defined? If it was defined, we have nothing because we don't deal with concentrated loads here. I think this might get confusing. You know what? Let's only define LKP points now and then deal with the loads later. The distributed loads are way more complicated. So for now, let's just make sure we define our LKP points and that's it. That's the only thing I want to do, define and add. Because I could have one LKP that is defined because it's the start of a distributed load. It's also inside another distributed load. So it becomes kind of crazy to deal with. So let me first of all do the definition alone and then deal with the distributed load alone. I think this is the best way of doing things. So I'll only define line key points for now. I think that's the best way to do actually, because we could have line key points defined for a concentrated load, and then we have a distributed load passing through it, which would cause all kinds of havoc if we don't capture that. So I think it's better for us here to just define line key points and then deal with all of them with the distributed loads. I think that's the best way of action. So here, if it was not defined, then let's define it. Yeah, that's the easiest way. So LKP start in this case equals LKP start location, right? It's called start location. So LK line key point start is line key point start location. And that's it. I will not define anything here. I will keep it for later. And I will put the LKP and just insert it. So here, wherever I see LKP, I must change to LKP start. And that's that. Yes, that's that. We added the starting point. Now I need to go to the LKP end. Wait, why do I have local loads here? Did I use it? I think I don't even need it. I don't think I would need it because I'm not adding any loads here. This entire block is not needed. Let's comment it out and think about it later. This is one of the heavier videos, but we're approaching the end, by the way. So LKP index, okay, let me see. So I'll copy this entire thing for the end. Let me just copy this entire thing from here all the way to here. Yes, I'll paste it again. And now we are dealing with the end. This is LKP end. Here, this should be LKP end was defined. This should be LKP end location, which means I need to use the relative location end. And now we think. So if the line key point, this is LKP end location. If that's the case, then LKP end was defined. And if it was not defined, then we define it. I think we are still okay. We define it at the end location, and then we input it. We put it in the correct position. Okay, fine, fantastic. So now we have our line key points. I think that's enough for today. So what have we done so far? We finished all the line key points that were added because the fem bars. We finished all the line key points that were added because of concentrated load on beams. We finished all line key points that were added because of distributed loads. And now we need to check, we need to apply the distributed loads and check which line key points are within the sphere of influence of the distributed load and add those things. So that is our mission objective. Okay, so now what remains after all this brouhaha is to deal with the load case, is to deal with the distributed loads on the load key points, because we have defined our load key points and now we need to check what kind of distributed loads are passing above the line key points, and we're gonna change the distributed before and distributed after accordingly. So that's gonna be another video for another time. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And with that being said, I want to give an LKP sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video. Bye bye.